Welcome back. So in the last module we started discussing on the foam heat sinks part, how to model them using how to come up with an approximate model, and we discussed this model essentially shown here on this slide, that a model for heat exchanger based theory that we discussed early on can be adopted for foams as well. It's just that we need to figure out a path to figure out its effectiveness, and that effectiveness, for that we needed a local or the interstitial heat transfer coefficient, and then the surface efficiency eta into A effective. So this we found that in there was a correlation that we can use for foams from Kalmadi and Mahajan, and then we started to discuss about how to map the foam into equivalent solid fins. So the idea here is that the geometry transformation, you don't use big transformation, it is just that equivalency is all is thought out. So the fin efficiency from a typical discussions you would have had in heat transfer courses is that now I have a fin, it has a certain thickness, and there is a heat transfer coefficient and T infinity known. The bottom is a T base or T wall, and then this top, let's assume for now Q double, that is it's an adiabatic tip. So for that, this expression is easily obtained. However, this typically is your m square term or m term, and depending on which book you refer to. So this m square is all that we need to calculate, and that is obtained from this, and this is essentially a parallel plate, a thin fin approximation or a single rectangular fin approximation from which you get. So the goal is to map this porous media into this equivalent. How do we go about doing it? So all you have to do is that equate the thickness to be equal to this thickness. There is a known, this K kappa or K sub P is the permeability of the porous medium. This is, as we discussed previously, is well documented. It is a geometric constant of a porous medium, and it can be obtained from any measurement of pressure drop of foams, and this is well documented. So for the given porosity and pores per inch or pore density, this is often given. So this for the given foam dimensions and the pores per inch, which is number of pores that exist for a linear inch, or pore density and the porosity, we obtain the value of permeability. So for the permeability, using the permeability relationship for parallel plate heat sinks, we parallel plates, we get the permeability expression. Then from there we calculate a thickness expression. Essentially the same thing can be used and for the getting this. So we use that expression TPF, which is the thickness of the porous fin, which was discussed here. This is the thickness. So we move this all the solids and into some n number of solid fins. We move the solid that is distributed in a reticulated manner into solid fins as an approximation, and we obtain that permeability, and from this we get a thickness. This thickness now is sufficient to calculate our efficiency, because we know the interstitial heat transfer coefficient, we need to know this. The solid thermal conductivity is to be known, because we know whether it is aluminum foam or copper foam and its thermal conductivity and what type of foaming process is used. So with this, and this h being the height, and with this now I know everything that I need to for calculating an efficiency. So calculating an efficiency becomes easy. So now I can calculate eta, I can calculate HF, I have values for HF. Substituting, this is also given, the A effective is given by the manufacturer itself, or one can estimate it using pores per inch and surface area per, using the specific surface area per volume. So the entire expression for effectiveness is known, then one can estimate the, and this model was, the results are not shown here, but then the model was compared against experiments, and it matched well within 12 to 13% with the experimental data. So this is an approximate model, but it works reasonably well for first order design or understanding how the foam heat sinks. But what we discussed so far is only the heat transfer part of it. The pressure drop can be easily obtained using the well known expressions. This expression for friction factor for porous media is also there, and this is also experimentally obtained. This is an empirical correlation. Here is an example correlation for foams. This 0.105 is a constant plus 1 by REK. This 1 by REK is a resemblance to Darcy's regime. In a porous media, you have Darcy regime and Darcy-Forsythe regime. This is the linear regime, and this is the nonlinear term that comes up because of the inertial terms. So this is also documented or empirically available. Just taking this friction factor correlations, and we can calculate a pressure drop for these foams, and these usually predict very well the experimentally measured pressure drop. Kappa here again is the permeability, phi is the porosity, u is the velocity, the Darcian velocity. So with this we complete the modeling exercise or discussion on foam heat sinks, and we will go to the last part of this heat sinks module, which is self-sustained laminar unsteady flow based heat sink or heat transfer enhancement. This is a concept that has been around for a number of years, and there was a paper by Carnier-Dawkins et al. On how to make use of laminar flow instabilities to obtain laminar unsteady flows. And this they showed that by using excitation of shear layer instabilities, one can enhance heat transfer 3 to 4 times compared to a conventional parallel plate. However, the pressure drop also would increase because of the nature of the unsteadiness in the flow. And so this theory, what we are going to do, this is not easy to discuss analytically or in any sense. We are going to look at it from purely from a phenomenological or mechanistic perspective. What happens? For example, if there is a flow, the idea of an unstable flow is created, or instability is created when there is a flow that enters, and as you can see, there is a groove here. When there is a groove, the flow gets separated and it recirculates. When the flow velocity or the mass flow rate is increased, what happens is there is a shearing layer here. There is a shear and you start to shed vortices into this stream. And at lower velocities, these vortices are shed, but they dissipate off very quickly. At higher velocities, this vortex shedding creates intense action of essentially unsteadiness. So as you will see in the upcoming slides, some idea you will get. Let's take for example a simple 2D geometry. This is a unit cell geometry where we look at flow coming in, and as it enters, there is expected to have some kind of separation zone here on the top and bottom. These are going to be separation zones, and the core flow will go through. The separation zone will start to interact with the core flow, and you will start to see an unsteady flow. And that is the idea, and it was simulated numerically to give some idea. And we look at the velocities and temperature at this point to see how whether they are actually whether they see unsteady flows or not. And so here is an example, is when the Reynolds number of the incoming flow is maintained at 500 based on the inner diameter, the hydraulic diameter, we calculate a Reynolds number. And you notice that at this low Reynolds number, the non-dimensional velocity, if I were to plot at that monitoring point, as a function of time, it starts to have some small wiggles, but these are not steady effects. But as I increase the Reynolds number, there comes a point called critical Reynolds number. This critical Reynolds number is where one starts to have this critical Reynolds number is where the unsteady flow effects can be clearly seen, and 665 turns out to be the case for this particular geometry, and one can see that the velocities are now oscillating up and down and they are steady, and this is for a small time duration, but you can run this for very long time duration, you will end up getting the same type of behavior. And as you keep increasing more and more, you start to see very steady flow at the, and you see a steady unsteady flow, meaning that a periodicity is maintained, and as you, and this unsteadiness is what is utilized to increase enhancement or increase the heat transfer rate from any of these cooling devices. So some of the commonly known structures that are there, for example, wavy shaped heat sinks that are commonly discussed, they have flow unsteadiness in them because they naturally, anywhere you create a separation zone, you start to see these type of effects. So the goal here, for example, was to to show you numerically at least that there is some kind of unsteady flow effects that one can encounter in these geometries. And as you can notice, for as you go from 500 to 665, at 500 there was small wiggles, but actually they ended up decaying off after some time, but we are not showing the time frame here, the entire time frame, but it decayed off. But at 665 the unsteady profile started to be maintained, but however as you increase more and more Reynolds number, you start to see a very steady flow effect coming out, and as you go to even higher Reynolds number, the nice uniform periodicity is now multiplied into multiple periods and chaotic flows started to happen. So here you start to see some kind of turbulence effects, but for us we are going to focus only around this range, that is where, because as you go into turbulent regime, the penalty in terms of pressure drop increase will be a lot higher compared to laminar unsteady flows. So the goal of any of these shear layer instabilities is to focus on the lower Reynolds number that can give you highest unsteady effects. And here's a instance from Reynolds number 1500. What happens is that flow enters, however, because of the shear separation zone on the top and bottom, the flow is getting diverted and it's getting squeezed, and this vortex from the bottom region is shed, and so it squeezes this flow, core flow, towards the top side, while the bottom side, the shedding is confined to the top region. In the next instance, what happens is that now the top layer starts to shed the vortex, while the bottom layer is now separating and is not getting. So now the flow, core flow, is now getting pushed up and down like this. And so here you can see more flow is going out on the top. Here you start to see the flow is squeezed to the, and in the next time frame it is this. So these are all towards a very small time single oscillation. Essentially we are talking about a single oscillation of this. So this is entire picture of how it begins. The next, the flow gets squeezed and it gets moved towards the bottom layer and gets more flow, core flow is exiting here. Then in the next instance, the bottom layer, bottom zone starts to eject the vortex and it starts to push this fellow up. So the core flow is moving up. Then eventually this flow, the bottom, as we started here, this is ejecting a vortex and it squeezes the flow to the top. So this completes one full cycle, and as you can see that this oscillation, if this is single period, if it continues, you start to get a steady unsteady effect, a periodic unsteady effect. And this is what is capitalized in these geometries where shear layer instabilities are used to improve heat transfer. But I didn't talk about how much improvement in heat transfer, but what you at least saw is that there is a an effect of separation is created, and the separated zone starts to shed vortex, and that pushes the core flow up and down, and that creates an unsteady flow. So, we will go and look into what the performance looks like in terms of heat transfer. So, what we are plotting is a Nusselt number as a function of time. A straight geometry will see this, and this is expected, and you can go look up what is a straight channel for the same hydraulic diameter and what its Nusselt number is expected to be. It's a fully developed flow, so you can get a Nusselt number for that. So, in a curved geometry that we discussed, if I were to plot the Nusselt number as a function of time, it has a very nice periodicity, as you can see, and it is almost twice that of the straight geometry. If I had a straight geometry, I would be getting somewhere around 7.6 ish, but here you are going to get close to very high heat transfer coefficient at close to 14, an average of 14. So, this is now plotted for as a function of Reynolds number, as a function of Nusselt number, average Nusselt number, and average Nusselt number. The average is obtained by averaging over the entire time. So, with circular arcs, or the geometry that we just discussed, this is called as a circular arc geometry. So, and a straight channel, the straight channel is going to give you this, and at 500 it is roughly same as the straight geometry. At 665 there is a minor decrease. This could be purely a numerical issue, but as you increase the Reynolds number, it start to see higher and higher values. One of the main things with this geometry, even though we didn't report the pressure drop, was that the pressure drop was higher, and we didn't discuss the pressure drop here, but the pressure drop tends to be much higher compared to a parallel plate geometry. Parallel plate geometries are ideal, and typically that is why they are still one of the workhorse in the industry, and they are quite good. However, if one needs to have a higher performance, then one can look into a hexagonal array of heat sinks, or rectangular array of heat sinks, or the porous foam heat sinks, or the self-sustaining oscillations. But the self-sustaining oscillations tend to incur very high pressure drop. So, one has to work with low velocities that still gives you high enough Reynolds number to trigger in shear layer instabilities and give you higher performance. While porous foam heat sinks can be shown to give you better performance than parallel plate heat sinks on a constant pumping power basis. So, what we have done till now is that we discussed the heat sinks into two parts. First, we focused only on the parallel plate heat sinks, and within the parallel plate heat sinks we discussed both sizing for natural convection and for forced convection. Then within the parallel plate heat sinks we looked into models, the common model that is based on 1 by eta into HA, and few others, and the other one based on the heat exchanger theory. So, after that we looked into few other heat sinks, the array of ducts, there we derived some expression, and it also looked like the heat exchanger based theory based. Then we looked into the foam heat sink, and then shear layer instabilities. Even for the foam heat sink, we made use of the heat exchanger theory to come up with an approximate model. So, with this we conclude the heat sinks part of this. So, as a total summary of the applications part, we started looking into electronics cooling as an application that makes use of convective heat transfer coefficient, or as a convective heat transfer for deriving heat sinking solution or heat dissipation solution. And then we looked at the introduction. In the introductory part, we looked at how heat is generated in electronics. then how the electrical leakage power, that is the power leakage power in the electronics, creates a challenging atmosphere where the leakage power itself is temperature dependent. And then we moved from that towards what kind of heat transfer coefficient should we use in an electronics cooling type system, where there are multiple heat sources with different heights and shapes and stuff, and how to assess what is the Reynolds number, what is the length scale, and how do I go about it. And we, in that module, will concluded that for such a situation we need to make use of adiabatic heat transfer coefficient. Adiabatic heat transfer coefficient uses an adiabatic temperature which does not depend on the fluid temperature, but it uses solid temperature as a way to assess and come up with an invariant descriptor for heat transfer coefficient. After that, we moved from that discussion towards the next module, which discussed on what is the enhancement. How do I assess if I were to come up with a heat sink or heat exchanger? How do I know whether what I am coming up with is going to be better than what is existing in terms of smooth structure? Let us say a pipe and or a tube that has some sort of fins that are introduced as a roughness element. Is this roughness element going to improve my performance, and under what conditions are they going to improve? Are they going to improve heat transfer, or are they going to compact, or are they going to reduce my pumping power, pressure drop? So that is what we formed on the third part of it. And then the final part, we looked primarily into all kinds of heat sinks. As I have shown here, the heat sinks lecture focused on these different aspects. And so what finally we conclude is that this concludes the applications part, and with this and the fundamental part we discuss a variety of aspects, and from the fundamental part we use some solutions or methods developed in the fundamental part, like the integral method, to obtain a solution for unheated starting length, and that unheated starting length was made use to come up with a new way of looking at the a problem of electronics cooling, where there are array of heat sources. So, we make use of the unheated starting length to come up with adiabatic temperature, and that we discussed as part of that second part of this applications module. So, with this we conclude the applications part, and I thank you for your attention and look forward to receiving any questions you may have. Thank you.